Welcome to this explainer. Today, we're going to skip the usual intros and drop right into one of the most fascinating and frankly fiercely debated scientific perspectives out there right now. We're exploring assembly theory. It's a concept that tries to answer a question as old as humanity itself, but it does it by mashing up physics, chemistry, and biology in a way that literally forces us to rethink the very nature of matter.
Okay, let's dive into this because this is absolutely the ultimate astrobiological mystery. Think about it. If we send a probe to Mars or Enceladus and it scoops up some complex molecule, how do we actually know if it was built by a living organism or if it was just some random lucky geological chemistry? We desperately need a new detective's lens, a mathematical and physical way to look at these molecules, and that is exactly where assembly theory comes in. It's a framework designed specifically to bridge that historical friction between the random, reductionist laws of traditional physics and the highly complex, intentional nature of biology.
Section 1. The Mystery of Life. Let's see how we build this bridge.
Section 2. What is assembly theory? A brand new perspective.
Assembly theory was developed through a really close collaboration between chemist Lee Cronin and theoretical physicist and astrobiologist Sarah Emari Walker. Their main idea is just fascinating. Life is the only mechanism the universe has to generate complex objects in high abundance. And this brilliantly illustrates what they mean. Sarah Walker loves to use this Lego analogy. Imagine you have a box of Legos to build the Hogwarts castle. It's a super complex model, right? If you just shake the box of loose pieces, how long would you have to wait for the castle to perfectly assemble itself by pure chance? Literally, forever. You need specific instructions and steps, reusing blocks you've already built to make larger sections. Well, chemistry is exactly the same. Looking at the assembly pathway of the adenosine molecule, you can see how complex molecules are built step by reusing simpler parts in a highly directional process.
This brings us to the first core pillar of the theory, the assembly index. The combinatorial universe, which is just a fancy way of saying all the possible ways to mash atoms together, is astronomically huge. The assembly index simply counts the minimum number of steps needed on the shortest path to build an object, allowing you to reuse substructures you've already created. Just like you can't shake a box of Legos and get a castle, nature cannot create molecules with a high assembly index without specific instructions. So the more complex the object, the higher its index, meaning more historical, ordered steps were required to form it.
But the assembly index alone doesn't give us the whole picture. We need the second pillar, copy number. Think of it like this. Finding one object with a high assembly index might just be a bizarre statistical accident, a one-off fluke in the universe. But if you find a high copy number, meaning a ton of identical instances of that same incredibly complex object in a sample, the odds of random chance building that exact same Lego castle 1,000 times in a row is basically zero. This is where the authors argue that having both high complexity and high abundance absolutely requires a specific selection mechanism or some kind of memory to replicate that structure.
Section 3. Measuring complexity. Shifting into the physical laboratory.
Now, what's really interesting about this slide is that this theory doesn't just live in the realm of abstract math or philosophy. It gives us a physical, practical tool in the lab. Assembly theory treats physical covalent chemical bonds as the elementary building operations. And the true beauty of this is that the assembly index can be physically detected and measured using techniques chemists use every single day, like mass spectrometry, NMR, or infrared techniques. By fragmenting a molecule in a mass spectrometer, scientists can literally infer its assembly tree. It gives us a robust physical tool that goes way beyond pure computational models. And through these physical measurements, researchers have established a truly fascinating threshold, the number 15. Based on tests with hundreds of biological, abiotic, and lab-created samples, an assembly index above 15 is considered the absolute threshold where it's extremely unlikely for objects to form abiotically, meaning without life. Only samples from living systems or technological systems produce molecules with an index above this magic limit of 15. So, according to the theory, we now have a physical, testable line separating non-life from life.
Section 4. Information, memory, and time. A profound shift.
Let's move to and see how this builds a profound philosophical shift in how we view the physical universe. Instead of seeing molecules just as static clumps of atoms, assembly theory sees them as entities carrying memory and historical information. In the traditional block universe of physics, time is just a background parameter, and objects are static. But here, time takes on a material dimension. Time is an object. Molecules are defined by their formation history, carrying their own evolutionary journey right in their design. The authors provocatively suggest that time is essentially the exact same thing as information and memory materialized into these objects.
Just look at this quote.
Each step in the assembly process of an object requires information, memory, to specify what should and should not be added or changed. In this framework, the physical sequence of building blocks literally represents memory and information stored right there in the matter. Without the memory of the previous step, you simply cannot accurately take the next step. The abundant presence of a complex molecule tells us that the universe somehow memorized how to make it. That is the very essence of selection.
Section 5. Adding, not replacing. A complementary framework.
Now, any new theory proposing to bridge physics and biology is going to face intense academic debate, which is totally natural and healthy in science. But we really need to understand that assembly theory wasn't designed to supplant or erase existing theories. Objectively, critics correctly point out that the math resembles algorithmic compression, like Limpel-Zierf or Shannon entropy. But assembly theory's unique complementary addition isn't about reinventing computer code. It's about mapping these computational concepts directly to measurable, physical, molecular bonds. It gives us a way to measure the importance of information and selection before genetic replication even existed.
So, the crucial point is that we should look at assembly theory as a vital addition to our scientific arsenal. It doesn't replace Darwinian evolution or standard computational physics. Instead, it acts as a much-needed bridge, a new physical metrology. It's explicitly designed not for data on a computer screen, but for the actual physical stuff we can shatter, weigh, and measure in a mass spectrometer, giving us a physical boundary where chemistry transitions into life.
To wrap up our explainer, this is the core takeaway. More than just debating the philosophy of what life is, assembly theory presents an exciting, incredibly practical addition to our cosmic toolkit. It turns finding alien life into a testable measurement. It diagnoses complexity through objective lab data, emphasizing the absolute importance of measuring molecules and finding those hidden patterns of memory baked right into matter itself.
And that brings us to a final, really profound thought. If time and selection can literally take physical shape through nature's molecular building blocks, what other hidden histories, ancient memories, and unwritten evolutionary stories are written into the very molecules that surround us right now? It's an absolutely revolutionary lens for reading the unwritten biography of our universe, something to definitely chew on. Thanks for joining me in this deep dive. Keep questioning the world around you, and I'll catch you in the next one.